Welcome, esteemed colleagues and guests. Thank you so much for joining this presentation today. We're going to be diving into what is, quite frankly, an absolute paradigm shift in space science infrastructure. Today, we're analyzing a major breakthrough announced by SpaceSeed Holdings and their consortium partners regarding two truly foundational patents. Now, we aren't just talking about a simple equipment upgrade here. We're looking at the actual deployment of autonomous AI researchers directly into orbit. So let's explore the architecture behind this monumental leap in extraterrestrial research.
Okay, let's quickly run through our agenda for the session. We'll start with the background in space constraints, then cover the shift to autonomy, break down Patent 1 and Patent 2, look at some real-world applications, and finally, wrap up with a future outlook. Let's dive right in. Section 1. Background and space constraints.
To truly appreciate the elegance of this solution, we have to first acknowledge the primary bottleneck in space research, the literal physical distance between human scientists and their equipment. Think about a standard ground laboratory. We have ideal conditions, right? Immediate intervention, essentially infinite bandwidth. If something goes wrong, a researcher can instantly judge a cell culture or just manually fix a fluid line. But contrast that with an orbital space laboratory. Out there, we face severe communication delays, highly restricted power, and absolutely zero human presence. Now, while we do have excellent automated devices up there already, like JAXA's AstroCell for remote solution exchanges, they still fundamentally rely on a human down on Earth, receiving the data, making a decision, and then beaming up a command. The human bottleneck is still very much a reality.
Section 2. The shift to autonomy. And this brings us to the core methodology. We are moving away from rigid pre-programmed automation and stepping into true LLM-driven autonomy. Just look at the standard scientific method loop. Observe, interpret, hypothesize, decide, and execute. Historically, humans have strictly owned those middle steps, interpreting, hypothesizing, and deciding. But the SpaceSeed Holdings Consortium is doing something incredible. They are using large language models to transplant that entire cognitive loop directly into the hardware itself. The AI actually acts as the researcher. It reads the microscope images, interprets the experimental states, formulates its own hypotheses, decides on the new parameters, and then executes the next phase of the experiment. All of this happens completely independently of Earth-based intervention.
In the academic literature, we define this as a self-driving laboratory. It's a fully closed-loop system. Now, we've actually seen some highly successful terrestrial precursors to this, right? Systems like Co-Scientist for chemistry experiments or A-Lab for inorganic materials discovery. But the breakthrough we are analyzing today takes this highly advanced closed-loop concept and hardens it specifically for the extreme, resource-constrained environment of outer space.
Moving on to Section 3, Patent 1, the autonomous cell device. Comparing these two technology layers brilliantly illustrates how complementary they really are. Patent 1, the cell device, is laser-focused on specific biological modules. Think of it as your specialized, localized operator. Its LLM handles immediate delivery and environmental decisions based on morphological adaptations. On the flip side, Patent 2 acts as the overarching neural center. It's an integrated OS capable of managing virtually any experimental module and coordinating cross-modal data across the entire satellite.
Let's focus on Patent 1 for a moment, the integrated autonomous experimental device for cell experiments. The hardware itself integrates a culture container, a microscope, and a highly precise fluid delivery system. But the true innovation, that lies entirely within its control unit. It continuously feeds multimodal data like microscopy images, temperature, pH, and dissolved oxygen levels directly into the machine learning model. If the LLM detects a morphological change in the cells, it doesn't wait for us. It dynamically adjusts the dosage of differentiation-inducing substances and alters the gas conditions in real time. It is literally a constantly self-optimizing physical experiment.
Furthermore, and this is absolutely crucial, the patent specifically addresses the unique physics of space. Down here in a 1G environment, fluid dynamics are pretty predictable. But up in microgravity, liquids and bubbles behave in entirely strange ways. This device actually possesses the specialized capability to detect microgravity-specific anomalies, like bubble contamination getting caught in the fluid lines. Using image and sensor data, the AI can autonomously decide to reduce the feed speed, pause the substance release, and execute a specialized purge routine to save the experiment. And it does all of this without a single prompt from Earth. Section 4, Patent 2, the Integrated Module OS. So if the device we just talked about is our specialist, this second patent functions as the laboratory director. Officially, it's titled the Experimental Module Integrated Control Device, and it serves as the overarching operating system. It relies on a common interface to connect incredibly diverse modules together, everything from cell culture to material synthesis. Through this common protocol, the LLM is able to cross-modally interpret images, numerical values, and operation logs from third-party modules. This is a game changer because it entirely bypasses the need for massive, expensive, custom software rewrites every time we send up a new orbital experiment.
Now, here is where it gets really clever. This architecture introduces a critical safeguard known as edge cloud collaboration. When the satellite is in a great position and orbital communication states are optimal, the system taps into highly powerful cloud and ground LLMs. But if it predicts a communication delay or one of those inevitable orbital blackouts, the OS automatically transfers inference authority straight to local edge models housed directly on the device itself. So the crucial point is that the scientific loop remains completely unbroken, regardless of where the satellite is relative to ground control.
Section 5. Applications and Joint Research.
The target applications here really demonstrate that this platform completely transcends traditional biology. Yes, the consortium is heavily focused on things like microalgae behavior, stem cells, and optimizing exosomes for next-generation medicine. But incredibly, the exact same autonomous loop is being applied to materials informatics as well. We're talking about alloy and semiconductor synthesis, alongside rigorous testing to see how extreme environments, like high radiation and hypoxia, actually affect these synthesis processes.
To give you some concrete examples of what's actually happening soon, SpaceNOME Lab is currently preparing for their late 2026 OABA satellite mission, which is going to observe the behavior and proliferation of microalgae euglena up in microgravity. Meanwhile, partners like IDDK and Regenesome are actively integrating IDDK's incredible lensless one-chip microscope technology directly into these space biodevices to study exosome production. These aren't just concepts, these are manifested hardware deployments actively scheduled for orbit.
In looking over at the domain of hard materials, SpaceSeed Holdings is conducting some fascinating joint research with Professor Yoshihisa Mori over at Okayama University of Science. They are applying this exact autonomous loop to a super high-pressure spark plasma sintering device. The AI proposes alloy or transparent ceramic candidates, the device physically synthesizes them, analyzes the resulting structures, and then feeds that data right back to the AI so it can propose the very next synthesis iteration. It's just a beautifully designed, completely closed loop for materials informatics.
Section 6. Conclusion and Future Outlook.
To really summarize the ultimate mission here, I want to direct your attention to this defining quote from SpaceSeed Holdings CEO Kengo Suzuki. He stated that the goal is transplanting the human observation, interpretation, and operation loop into the device itself, turning space into a research infrastructure. I think that encapsulates this philosophical shift perfectly. We are watching space transition from a highly hostile zone meant for exclusive, one-off experiments into an accessible, continuous industrial research infrastructure.
Of course, getting there takes work, and the consortium has outlined a rigorous step-by-step roadmap to bring these patents off the drafting table and into actual orbit. Step 1 is completing their ground environment closed-loop validation. Step 2 involves simulated microgravity testing using devices like a clinostat. Step 3 is all about stress testing that local edge inference under severe, simulated communication constraints. And finally, Step 4 is the actual orbital implementation of their ultra-compact space experiment module, which they've dubbed SpaceAgent.
Which leaves us with this final, highly compelling question. What is going to be the very first major scientific breakthrough discovered entirely by an AI researcher in orbit? Will it be some kind of novel longevity drug synthesized from zero-G cell cultures? Or maybe a next-generation superalloy forged in the vacuum of space? Whatever it is, the infrastructure is being built right now to find out. Thank you so much for attending this presentation today. I really hope you leave this session as eager to witness the future of space laboratories as I am. Have a great day.